few stragglers. Okay, welcome everybody to the first CAIDA seminar of October, I guess. Today we have Naman, who's a research scientist at Google AI in Princeton, which is a relatively new Google AI lab. He did his master's at UIUC and then did his PhD with Elad Hazan, who is someone many people of us know. And Naman has just worked on an absolute ton of topics related to machine learning, scientific computing type of stuff. So things like asymptotic rates for non-convex optimization, things like second order methods for machine learning in distributed settings, regret learning, semi-definite programming, lower bounds, all sorts of stuff. So I'm looking forward to the talk today because I have no idea what a non-stochastic control framework is.
Okay, awesome. Thanks, Mark. Right, let me just switch to the application. Okay, so you guys can see the slideshow, right? Okay, yeah, thanks everyone for coming. My name is Naman. I'm a research scientist at Google AI Princeton. It's a sort of a small Google AI lab, which started a couple of years ago. And about a couple of years ago is when we started to sort of think about this non-stochastic sort of control problem, sort of marrying control and online learning. And now we call it the non-stochastic control framework, and that's what I'm going to talk about. Let me just begin by thanking my collaborators. So this is Nadli, Brian, Alad, Sham, Karan, and lots of other people in the lab right now have also sort of done follow-up work, which I'll mention on sort of building on the ideas that we built up on this non-stochastic control framework. So just jumping in, I mean, what's sort of the focus of the talk or this work is just controlling dynamical systems, and sort of control of dynamical systems is basically ubiquitous. Anywhere there's a machine or a robot around us, you need some kind of control mechanisms in there to achieve various tasks. There are sort of more niche popular sort of applications that have been coming in, and things like autonomous vehicles. For a company like Google, there are applications of control of dynamical systems in data center cooling. And then something that sort of particularly my lab's been working on very recently is this sort of inspired by the pandemic that's around us. We've been looking at this control of medical ventilators. I'm not going to be talking about them, but hopefully you'll hear about it soon enough. Okay, so what's a dynamical system? Well, before I'll sort of define it formally, it's just basically any system that you can that maintains some kind of state, and you can sort of push or control with some kind of input, right? And sort of just before I sort of define our work, what's kind of like the motivation for our work? Well, I mean, control theory has sort of existed since whenever. And we sort of wanted to think of like, what does control mean in the age of machine learning? And one of the things that we're going to target sort of particularly in this work is going to be the idea of robustness, something that's very, that's been sort of like robustness is, it can be said that it's kind of like a success story of like present day machine learning. And the other success story is basically very, very simple algorithms. Think something like gradient descent. They tend to sort of lead to very robust solutions and sort of tend to be efficient in like the large data regime. So we want to sort of rethink the notion of robustness that exists in control, borrowing ideas from like online learning, gradient descent, and pulling these algorithms into this space. That's sort of like the motivation for this work. One sort of nice quote that we keep sort of mentioning in our talks is we got this quote from one of the reviewers in one of the review cycles. Says like, as opposed to deep learning, control got us to the moon. Okay, so I'll just dive right in, and sort of the first part of this talk is going to be about online control with adversarial perturbations. And I can just at this point just sort of set it up completely. So let me begin with sort of defining what a dynamical system is. So a dynamical system is just any system that holds a notion of state given by these vectors x. What you can do to the system is you can provide a control input given by this variable u, and sort of the system accepts some sort of disturbance, perturbation, whatever you want to call it, So there are three things at any point of time that go into the system, X, U, and W, and the system sort of transitions to a new state based on a fixed function of these three values. So there's a slight typo here. This doesn't need to be necessarily a sum. It's actually xt, comma ut, comma wt. Apologies about that. And sort of what do we want to do with such systems? One particular task that's quite popular is the task of what's called optimal control of such dynamical systems. And herein what you want to do is basically you want to design a sequence of control inputs that minimize a certain cost, right? So think about, like, say you're flying a drone, and the cost could be sort of, like making your drone reach from point A to point B. So sort of distance to point B could be some notion of cost that you're at. So it depends on the state you're at. It depends on the control input you're putting in. The motivation for the control input you're putting in would be something like, say you want to make a drone fly from point A to point B. How would you do it with sort of the minimum amount of energy consumed or something like that? Okay, so that's it. So that's the problem of optimal control of dynamical systems. At this point of time, I'll sort of make a restriction, and for the rest of the talk, or rather most of the talk, we're only going to be focusing on this sort of canonical but sort of very, very interesting subclass of dynamical systems called linear dynamical systems. So the main sort of specification here is that the next state is only a linear function of your present state, and a linear function of your present control that you put in. Okay, so here is sort of what we're going to focus on for the rest of the talk. Also, I should have said earlier, feel free to sort of jump in with questions. I guess you could just write in the chat and sort of Aaron will tell us, or you could just shout in. Either of those work. Okay, so that's the setup. And sort of let me just give a sort of very, very high level overview of what's relevant to this talk, sort of highlights of optimal control. And sort of one canonical sort of main result in this area is this idea of a linear quadratic regulator. So imagine that the perturbations that are coming into the system are generated by an independent Gaussian process. So WT is sort of independent of everything that has happened before and is generated by some Gaussian, and sort of your costs are some quadratic function. Okay, so this is sort of a very important subcase, something which leads to very rich theory, something which has been studied for decades. And the solution, when you try to find sort of the optimal policy or the optimal sequence of controls, turns out to be a linear policy. So what you need to do is sort of, you need to find sort of the optimal matrix K that hits the state and gives you your sort of action at that point. Okay, so this is kind of easy to see why this happens. I mean, you could write down sort of like what's called the value function at a particular state and sort of do a backward induction. And like if you assume sort of the value function of the next step is a quadratic, it's easy to show that the value function of the step before remains a quadratic. This thing then just unfolds on itself, and you get this very nice result. Okay, so this is sort of like the canonical sort of result that we know from optimal control. And sort of what's kind of restrictive here is these assumptions that are there on
Naman, there was
yeah.
a question in the chat, which is, are you focusing on the steady state, or are you focusing only on the steady state?
So most of the talk I am going to be talking about like a finite time system. But right now, while describing these, I'm describing the LQR solution for a steady state. Yes, that's correct. Okay. Okay. So yeah. Right. So these assumptions that sort of independent that the system gets an independent Gaussian noise and sort of costs are quadratic. These are kind of restrictive assumptions, and sort of optimal control theory has sort of tried to relax these assumptions in a very worst case notion, which is usually given by something like this. So like suppose I like assume for now that you're going to do the worst, like nature's going to give you the worst possible perturbations in some bound. What is sort of the min max thing that you can do? What is the best sequence of controls that you can provide, assuming sort of nature gives you this sort of worst case instance? So this is often called H infinity control. And this is what's this is what sort of the notion, like the primary notion of robust control. And sort of what, looking at this notion, if you look at this, like this min-max structure of H infinity control automatically sort of reveals itself to be pessimistic, right? So you're designing your sort of control inputs to be guarding against the worst possible thing nature can do against you, right? So it is kind of like a fairly pessimistic notion, and it also tends to be quite computationally ill-behaved when your cost functions are not quadratics. So even if these cost functions are convex, the solution tends to be quite computationally ill-behaved. This notion is also not adaptive, in the sense that imagine you sort of planned against the worst case, but say nature was not that adversarial, managed to give you something very nice, the sequence of perturbations were nice, or in fact zero, like then you might still have a bad solution because, well, you planned against the worst case, right? So what's sort of what we found missing from this notion of H infinity control is, like, from the world of sort of online optimization, is can we sort of get something similar to what we call regret there? It's like an adaptive performance metric, something that depends on how good or bad these W's are going to be, and can we get a result that says if the W's are good, let's perform well; if the W's are bad, let's do, say, as bad as something like H infinity control. Okay.
And there's some discussion in the chat over whether U is discrete. Can you expand?
Sorry, what's the question?
So let me just, so in the chat, they're just asking if U is discrete or continuous. And then recently someone also asked about discrete, whether it's discrete or continuous time too.
Right, so we are going to be only working in the discrete time scenario, and U sub, the R sort of, the space of U and X is, the best way to think about it is, let's say they're R to the D, or some subset of R to the D. So they're continuous spaces. U and X live on continuous spaces, and we're only going to be focusing on discrete time here. Okay, yeah. So you want to get to this notion of sort of this adaptive notion of robust control, and we also want to get it for sort of general losses, like going beyond quadratic losses. The reason for that is sort of, if we want to bake in constraints, the natural way we know how to do that is like sort of build them in your cost, build them in your cost with some kind of barrier functions and things like that. So we want to get to sort of getting things for like general convex losses going beyond quadratic losses. Okay. So just giving a motivating example for something like this, like I said, like a canonical problem here could be, say, you want to fly a drone from some source to destination, and say like you modeled the drone perfectly, but then when you go out in the world, there is unknown weather, there could be wind, rain, all kinds of other uncertainties. And sort of there is absolutely no reason to model that as some kind of non-stochastic thing. I mean, wind is clearly non-stochastic. If wind is high right now, it's quite likely wind was high sort of just a second before. And sort of what this sort of optimal sort of like robust control theory does is that it tries to model all possible wind conditions under, say, a bound, right? So like the wind could be as bad as possible. And what we are trying to target here is sort of adaptive control, which gives sort of the best of both worlds. It's sort of efficient and fast when weather allows it to be that way, when wind is, say, small or sort of is pretty random, but sort of we want to get to a notion that's kind of optimal to like the actual instantiation of the perturbations that you saw through your run. Okay. And yes, of course, we want to get to, since we're theorists, we want to get some kind of finite time provable guarantees. Okay, so with all of these motivations, I guess I can now sort of describe what sort of the main problem we're going to be focusing on. So remember, this was the optimal control problem like we had described it. You're trying to minimize some kind of costs, trying to design a sequence of control inputs, and your system evolves in this fashion. The main sort of key things that we want to add onto this sort of non-stochastic control setup is that there is adversarial noise in the dynamics. So there is absolutely no, there is no particular process that generates this. WT can be sort of can be chosen in whatever fashion. And we want to keep C's to be, the costs to be convex. At this point of time, let me sort of say some assumptions that I'm going to make for the rest of the talk. I'm going to assume that the system is known. So I'm going to assume that you know A and B in advance. I'm also going to assume that they are time invariant. So A and B sort of remains fixed through the run of the system. And I'm also going to assume this thing, this special case of full observation, which says that I get to see the entirety of the state. Okay, so I get to see the exact x sub t at every point of time. Notice that if I get to see x sub t and I know the system, I can just use this equation to sort of get to know what w sub t as well is, right? So like sort of being full observation on x sub t sort of just transfers over to full observation of w sub t. So I'm kind of going to assume full observation of x sub t and w sub t. All of these assumptions, known system, full observation, and time invariance, have been sort of relaxed to sort of pretty high degree in sort of follow-up work from our group. And I'm going to point to that work sort of towards the end of the talk. So that's the setup. And what we want to do is we want to set up like an online game for this sort of adversarial non-stochastic control scenario. So imagine that there are two players, the blue player and the red player. And at every round T, imagine it's a capital T sort of round game. And at every round T, your blue player is your controller. So it chooses a control, U sub T. Your red player is say an adversary that chooses a cost function. Okay. So C sub T is a convex cost function on X comma U that your adversary chooses at every point of time. And there is this dynamical system that exists at state X sub T. Once the sort of the blue player and the red player lock in their choices, the system advances to the state x sub t plus 1 based on the control that was provided in by the blue player, and the blue player suffers the cost that was given by the red player. So there was an xt, there is a ut it chose, and it gets the cost. For people who've not seen online learning before, just a clarification, the blue and the red player sort of choose at the same time. So red is choosing without seeing U sub t, blue is choosing without seeing C sub t. Okay, so that at every round, they commit to two things together. The system transitions and the blue player sort of gets this cost, right? So that's the game. And what is our goal? We want to we are, let's say, the blue player, and what we want to do is we want to minimize this notion of policy regret. So what is policy regret? Let me define that a little bit carefully. So of course, what do you want to do? You want to minimize the cost that you suffer, right? So I mean, at the end of the day, the goal is just minimize the cost that you suffer. But how do you sort of compare yourself to like what could have been done? What is the optimal thing to do? So this policy regret says, imagine you've got a policy class. So a policy class maps the history that you've seen so far to a control action. So what you want to do is you want to minimize your costs such that, like, with respect to some fixed policy in some policy class, you are sort of not far away from what the hindsight minimum is going to be. Okay, so this is the policy regret term. What's kind of important to note here is that policy regret tends to be counterfactual. So what you are going to suffer today depends not only on what you committed today, it also depends on what you committed in the past. That comes in because of this notion of state. The cost depends on the state, and the state that you reach at any point of time t will depend upon what control input you provided before. Okay, so what is on the right hand side of the comparator is a counterfactual state sequence. So imagine in hindsight I was playing a policy pi, what states I would have gotten to and what control inputs that it would have led to. You want to minimize against that benchmark. Okay, so this is where it sort of differs. If you've seen sort of online convex optimization formulations before, the typical ones don't have this counterfactual notion. I'm going to define it again, but like this is sort of the main point. There is a certain in control or sort of in reinforcement learning, there is this notion of policy regret that you want to minimize against. Okay.
So a quick question is, does the blue player get to see the cost function or just the cost value at that point?
Good. So for this part, I am going to assume that you get to see the entire cost function.
Okay, and then
I
unrelated.
mean, eventually our, sorry, what was it? Sorry.
Oh, an unrelated question is, so these x tilde t, are you also optimizing over those?
X
Sorry,
tilde
I'm
or
sorry.
X hat. So sort of, I'm confused what
Yeah,
X is.
are you also minimizing or maximizing over the x hat values?
No, 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 no. So what you're doing, so how is X hat defined? You choose a policy from your policy space in hindsight, right? And then you sort of run the system complete to sort of a t time step. So that would lead to a trajectory, right? So your own, and then there will be a cost of that trajectory, and you minimize the cost over the policy space. Okay, so the main really just lives on the pie, on the policy.
And one more question is, who selects WT from the chat?
Good. So that is what was going to be the next point. So as of now, I have not said what is happening with W sub T. So let me just say what we're going to do with it. So this is the notion of policy regret. And I want to bound this notion of policy regret over any selection of W1 to T. Okay, so as long as each W sub T is bounded by say 1, this one is of course arbitrary. Say it's bounded in L2 norm by 1. I want to sort of minimize this regret with a max outside on W1 to T. Okay, so whoever selects W, like however you select W1 to T, you can sort of know everything and select W1 sub T. I want to sort of have this value to be as low as possible for every W1 to WT. Okay, so here is where sort of the differentiation with H infinity control happens. I am giving this guarantee for every sequence of W1 to sub T. Okay, so what I'm going to say is that my cost that I suffered is as good as it could have been in hindsight for every sequence of W1 to T. Not so if indeed the cost could be very low for a particular sequence of W1 to T, the guarantee will tell me that yes, my total cost is also low. Okay. So that is sort of the framework. I'm going to stop here for like maybe a few more seconds just to remind you the sort of salient points here are the costs are convex. It's a known time invariant system and full observation.
One more question from the chat is, does this mean the player is being as pessimistic as possible?
Which player? I guess the question's about the blue player, maybe.
Blue player, yeah.
No, in fact, like it doesn't. Like I'm not sure why it means that they're being as pessimistic as possible. Like they want to sort of just minimize. Like our goal is just to come up with a strategy that keeps this notion of regret as low as possible. It could be that the strategy is highly optimistic. It could be it's pessimistic. Again, let me just stress, it is an instance-wise notion, right? So I want to the difference is that I'm not taking the max over just the cost. I'm taking the max over the distance from the optimum, right? So for every sequence, I want to be like a certain amount close to the optimum. So imagine this regret I can show to be 0. Then what I'm saying is that however the W's are chosen, I am as good as I can be in hindsight. Right? So of course the regret's not going to be 0, but like that's what this notion means.
Okay, I'm going to give you one more question, but then I think we're going to have to let you talk a bit more, which is how would the best policy under this scenario do against an H infinity metric?
Right. So let me just clarify this is actually a generalization of the H infinity metric. So let's think about it. So imagine in the H infinity metric, the inner maximization happens on a particular sequence of W1 to sub T. Then for that sequence, what you have played is still optimal with respect to with respect to the optimal policy on that sequence. So in that sense, till this point of time, this notion of policy is actually more general than H infinity control. It's giving you sort of instance-wise optimality, and of course, because it's giving you instance-wise optimality, it's giving you something as close as up to the sort of the bound that you get on this policy regret. So like say this is less than equal to epsilon, you will be sort of epsilon closed, even in the H infinity metric. Okay, so I'll just move on now, if that's okay. Okay, so far I've been just talking about generic policy classes. So what's a reasonable comparator policy class? Like we said, sort of if we looked at a Gaussian sort of linear dynamical systems with quadratic costs, the sort of a canonical class of policies that emerged was this class of linear policies. So what you're going to do, what you do is that at any point of time, the control is a linear function of the state. Let's call this pi sub k. And what we want to do is, like, this is the policy class we are going to stick in our previous notion of regret. So we want to be optimal against this policy class. What we'll actually get, like sort of our aim is that, so let's remember our aim is that, what we're going to get is a slightly more general notion. Like what we get is this notion of what's called disturbance action controllers. These allow sort of, I'll define them formally in a bit, but these allow sort of our policy class to be more general than just a linear policy. It allows it to be sort of a linear dynamical system by itself. And sort of these disturbance action controllers are defined as just basically the policy is given by sort of m linear functions, t linear functions, which are all called m1 to t. And the action that you're going to play at any point of time is just a linear function of the wt minus I. So remember, as I said, we have full information of wt minus I. I can play a policy that's a separate linear function of each of these wt minus I. Right? So in a bit, I'll show why this policy class is a generalization of sort of the linear policy class. So let's call this pi sub DFC for disturbance feedback controllers. And let me just say what the main result that I'm going to show is that, remember the notion of policy regret. With respect to this class of disturbance feedback controllers, what I'm going to show is that for any sequence of W1 to T, such that each Wi is bounded, this regret is bounded by at most something like O of square root T. Okay, so that's the main result. It's going to be algorithmic, so I'm going to give you an efficient algorithm. And what do I mean by efficient? It's going to be polynomial in all the natural system parameters, and it's going to be logarithmic in time. Okay. So I'm just going to pause here for like 1 second. There is an asterisk to this result. I'm going to assume the system is strongly stable, and I'm going to define what I mean by the system being strongly stable soon. But this is sort of the main result of the first part of the talk. Okay. So, okay, so before sort of jumping into how this result comes about, let me just give a quick sort of a primer over online convex optimization. So what happens here? You're given a convex set chi, and again, there are blue players and there's a blue player and there's a red player. So what I'm describing, so I should step back for a bit. What I'm describing here is a canonical online convex optimization setup, something that's sort of maybe some people are already familiar with, but I want, like, some people might not be familiar with it. So I kind of wanted to give an introduction to that. So you're given a convex set chi, and sort of the blue player is outputting some vector inside this convex set chi, x sub t is inside chi, and the red player is choosing a convex function which is going to act on this x sub t and give a cost of c sub t x sub t to the blue player. Okay, so this is happening at every round. Again, this cost is convex. And the goal in typical OCO is that you want to minimize a similar notion of regret. Like, I call this normal regret because it's an easier notion, and I'm going to specify why. But particularly what this regret notion says is that you want to minimize cost compared to the optimal single vector you could have played in hindsight. Okay, so this is what typically is defined as regret. Notice the main difference from our notion of regret, which I call counterfactual regret. Here, the cost that you suffer at any point of time t depends only on the commitment you made at that time t, right? In the previous thing, in the counterfactual notion, sort of what you're getting now depends on what you did in the past as well. Okay, so this is the notion of sort of normal, like the typical notion of regret. And a very, very simple canonical algorithm gets you to sort of the optimal thing that you can hope to get here. And the algorithm is just called online gradient descent. At any point of time, you have your x sub t, you update it by just taking a small step in the direction of the instantaneous gradient of the cost. Okay, so this is a simple canonical algorithm, and what you get out of this is that you get this you can show that the regret is bounded by square root of t. Another thing, let me just point out, why are these numbers square root of t important? Like, think of the average regret, or like sort of like the sort of think of dividing both sides of this equation by t. So what you're saying is that on average, the regret that you're suffering is going down as a function of t. And in the area of sort of online convex optimization, the optimal rate this average regret can go down is by the rate of something like 1 over square root t. Typically, without any assumptions, this is the sort of optimal rate that you can get it down to. And this very simple algorithm called online gradient descent achieves this. Okay, so then let's just sort of get into our sort of result. So the first ingredient that goes into the result is this idea. Okay, so I mean, I want to reduce everything to online convex optimization if possible. So remember that so as I said, I want to focus on this policy class of linear policies, pi sub k, right? But the problem with pi sub k is that if you parameterize it as its natural parameterization in terms of this matrix k, what you get is that the sort of action you're playing at any point of time, sort of by definition, it is equal to k times x sub t plus 1. But if you sort of roll this equation down, what you're going to get is that the action sort of looks like this function on the right here, right? So in terms, if you view this as a function of k, this looks like some weird polynomial as a function of k. And if I'm looking at a convex cost on top of this action, there is no sort of reason why this should look convex at all, right? Like if I have a convex cost over this right hand side as a function of k, I'm not going to get any convexity. So I want to move to the space of convex function. And the way we do that is sort of by doing this improper relaxation. So what we're going to do is, just staring at this a little bit, what you can do is that you can nevertheless, like if you look at the expression for u sub t, when you play a linear policy, it is at the end of the day some linear function hitting the disturbance that you supplied I steps ago, that was supplied to the system I steps ago, right? So I can take this sort of k times this sort of big summation that's coming in, and what I can do is I can wrap it all up into a single matrix m sub I, and I can parameterize my policy not in terms of k, but rather in terms of just these linear functions, m1 to m sub m capital T, right? And if I sort of play this like this notion of inner product, which is just basically summing sort of the linear functions that are hitting these wt minus I, this is a more general class of policies than linear policy. Okay, so this is why we focus on this class of policies called disturbance action policies. And the main sort of benefit that you get here, you can clearly see now, because your action is so your variables, the parameters that you're working with are these m's. This is what you want to learn, right? So your action is clearly now a linear function of your m. So if I put a convex function on top of it, it still remains convex. So what happens then is, under this reparameterization of linear policies, what was in my comparator becomes completely convex, right? So I have moved my problem from being, so like the non-convexity in this problem was possibly fake. If I just do this sort of very simple relaxation, you move to the convex world immediately. Okay, so this is sort of the first main idea that sort of motivated this work. Just parameterizing with respect to disturbance action policies gets you back into sort of the convex land. Okay. Okay, so then let me just look at the game again, and let me in under this reparameterization of policy, let me just restate the game again. right? So what is happening is that at every point of time, our blue player now, instead of like saying picking an action, it picks say T matrices M1 to MT, right? And the action that is played is just a linear function, these M matrices hitting the disturbances at the appropriate time step, and the state then transitions. Okay, so you get the same notion of cost, you get the same notion of state, but only that the action, instead of playing an action, you're playing these sort of this parameterized through this parameterized policy class. Okay, and now that we can do this, we can redefine a notion of policy regret, and sort of instead of comparing to say linear policies, I can compare to say the best optimal M star. Remember, M star is going to be say capital T matrices, but I'm going to compare myself to the optimal M star in hindsight. Notice that my comparative, like what's on the left hand side is my cost that I'm going to suffer. What's on the right hand side is as a quantity that's potentially smaller than had I just done a min over linear policies, right? Because this policy class contains the class of linear policies, I've sort of made my problem harder by sort of replacing the min on the right hand side with a min over M star. Okay. So there are two images. So, okay, good. So things starting to look convex. We've gotten this reparameterization. So what's the problem? There are two problems. Firstly, there is an immediate problem. There are potentially too many parameters in the system. So like you're looking at matrices and you're looking at T of them potentially, capital T. Let's say your game is being played for capital T rounds. You're looking at potentially capital T parameters. And that's bad. Like usually you would not get like regret scaling as something like sublinear in time if you've got so many parameters. So that's problem number one. And sort of a more important problem is that unfortunately that original thing of counterfactual regret, like what you're playing right now, like what you're suffering right now, X sub T, still depends on what you have done in the past. Okay. So these are two problems that remain that sort of differentiated from directly applying, say, an online convex optimization result. And let's resolve these problems now. So first, let's resolve the problem of having too many parameters. And it turns out it will kill both birds with the same stone. So the idea here is sort of to enforce some kind of a notion of stability. What's it basically saying is that I want my sort of the state that I have gotten to right now to depend only on potentially a bounded history, right? So I want my system to decay over time. And the notion we use for sort of having to formalize this notion of decay is we want our system to be a strongly stable system. So a strongly stable system, by definition, this was defined by, I should have given a reference here. The reference exists, appears later in a paper by Cohen et al. So the idea is that you want to, as long as there exists a matrix K, such that if you look at this matrix A minus BK, the spectral radius of this matrix is bounded away from 1, right? So delta is positive. I want the spectral radius of this matrix to be bounded away from 1. Another way to think about it, a natural assumption that people typically put is that they put this assumption directly on the matrix A. So think of like, say, replace spectral radius by spectral norm if it's a little easier to think about it. And imagine putting it directly on the matrix A. What you're saying is that A square, A cube, and for the powers of it decay exponentially fast, right? So what you're doing, instead of just applying this matrix, putting this assumption on the matrix A, what a more general sort of assumption that we're going to make is that we're going to put it on the existence of a stabilizing controller. This is often also called the existence of a stabilizing controller. So since you know A comma B and you know that your system satisfies this property, you can begin with sort of the knowledge of at least one stabilizing controller. Remember, there could be many stabilizing controllers, right? And this K matrix lives in the same space as the space of linear policies. So what you're trying to do is sort of pick maybe say an optimal stabilizing controller for your system. You need to just begin with the knowledge of one stabilizing controller. Okay. So K is, say, any stabilizing controller for this system A comma B. And now what you do is that you the action that you're going to play is going to just look like K times X sub T. So it's K times hitting the present state that you're at, and this disturbance feedback policy. But now I'm not going to roll this disturbance feedback policy all the way back in time to time 0. I am just going to roll it to a finite horizon of size H. Okay, so this is where I'm sort of reducing my parameters. Earlier, I would need sort of mi to go from sort of, say, time t to all the way time to time 0. I'm just going to roll this down to sort of a fixed parameter h. And what you can show is that if you choose this h to be, say, inverse in delta times log t, it can sort of emulate any stable linear policy. Like this still this still has enough representation power to sort of replicate any linear stable policy. Okay, so that's property number 1. Property number 2 is that knowing that sort of K is a stabilizing controller, adding this little piece K times XT allows your policy to be forever stable. Okay, so any disturbance action policy, as long as these matrices M are bounded, can be shown to be forever leading to sort of like you never get a blow up in states. And that's kind of like the main problem you're trying to avoid here. Okay. All right. So then going back to the sort of game we had this problem of too many parameters, but now we can sort of fix it by sort of this just rolling it back down to only, say, log t steps. So now at every point of time, the player is committing to only h possible things. And sort of your comparator class has also become sort of m star, which only has like h matrices. Okay, so that has fixed the problem of potentially too many parameters. But still the other problem remains that x sub t at any point of time depends upon everything you've played in the past. Okay, so that's the next problem we're going to solve. And this sort of happens very naturally through a framework that was introduced in a paper of Elad Hazan a few years ago. And this idea is called like online convex optimization with memory. And herein, basically what's happening is the following. Notice that if I have this property of like only playing stable controllers, or sort of remember what we did was we sort of made our policy K, like sort of added this K times XT to our actions. And sort of the result, what happens with respect to that is that the cost, what you can show is that the cost you're suffering at any point of time depends only on a finite history of your actions, up to a small error that can be ignored. You don't need to sort of worry about what you played, say, a long time ago in the past. You only need to worry about what kind of policy you played, say, H steps behind, or in this case, actually Q steps behind. Okay?
Naman, there's a question in the chat.
Yes.
Which is, do you need an assumption on the sequence WT?
Yeah, the only assumption that we're making on the sequence WT is that every W sub T is bounded in, say, L2 norm. And of course, all the constants that are being thrown around, which I'm hiding under the O of notation, sort of include that bound, right? So it's all polynomial. It's like it appears polynomially in the bound. In fact, it appears maybe just as a whatever, like as a linear function, but like that's the only assumption we make on W. Okay, so then since the cost at any point of time depends only on, say, a fixed history of actions, this very nice paper of Hazan Anava et al., Elad was a co-author on the paper, gives you this nice notion of comparing yourself. Like, so you get two properties. You get that the function, like the cost only depends on your past Q actions. And it also, it's easy to show that it depends only in a convex fashion. Like convexity remains preserved. And what you get is an online convex optimization problem where sort of every time an adversary is choosing a convex function that penalizes your past Q actions, right? And you want to sort of compare yourself to like the best fixed policy action that you could have taken. And what you get, this sort of nice result gives you that you get the square root t regret rate back, except with, say, a multiplicative factor of q, right? So the only sort of issue that this additional sort of dependence on h things, or rather q things, causes is an additional sort of constant factor of q. And remember, what we can show is that this q somehow scales logarithmic in t. So this is not going to sort of like my results are actually, I should have stated, it's all O tilde of square root t. I'm hiding log factors everywhere. So up to sort of just this log t factor loss, I can easily handle sort of actions depending some amount of history in the past. And the algorithm tends to be pretty simple here. You will still do gradient descent, but what you do is you do gradient descent on this modified cost function. Remember, this modified cost function is this f sub t as a function of your past q control actions. Think of just playing an action and taking a gradient with respect to a fixed action in all of those. So imagine what you're doing is that you sort of at every point in the algorithm. So at this point, let me just actually show the algorithm. But before I jump, sort of the reason why such a result actually happens is that you can, like, the way any regret algorithm works is like OGD or something like that, online gradient descent, has a certain slow moving nature. It does not move too fast. To get sort of low regret, you cannot have sort of very quick movement. That's just natural. So anything that gets low regret has a slow moving nature. And sort of if you exploit the Lipschitzness of your cost function and the slow moving nature of OGD, you get that you do not suffer too much, even when depending on actions in your past. So here's the algorithm, but let me sort of, the final algorithm, which we call the sort of gradient perturbation controller. Let me summarize what this algorithm is doing at any point of time. What you're doing at any point of time is that you sort of reset yourself to, say, 8 steps back in time. You go back 8 steps back in time. You think that you're going to play, say, a fixed policy action. So by policy action, I mean this sequence of M's. So I'm going to play the same sequence of M's across time through these 8 steps. And then I got the cost that I suffer at this moment, at this point, which is not equal to my present cost. It's only a fictitious cost, but it is close to my present cost. I can take a gradient through that cost. And we take a gradient through that cost, and that's what the algorithm basically becomes. So if this is unclear, I promise you, just like if you, I'm happy to sort of take questions after the talk, but this is really a simple idea. It just looks a little bit complicated right now. All you're doing is sort of just fixing an action from 8 steps behind, hallucinating a cost function you would have gotten had you played the same fixed action from 8 steps behind, and then taking a gradient descent step with respect to that. Okay, so that's the gradient perturbation controller, and that algorithm is what gets you this sort of low regret rate with respect to this counterfactual regret notion that we had defined. I'm just going to quickly jump onto some experiments we have because I'm kind of short in time, but so here's sort of simple settings, and sort of let's see how this GPC algorithm performs. So suppose you've got a linear system and you've got like your standard Gaussian perturbations. In this case, you know that LQR is the optimal solution. What we show is this is kind of like a sanity check. GPC does almost as good as LQR in this setting, as it should. I mean, it cannot do better than LQR because LQR is optimal. Notice that GPC has some notion of regret associated with it. So we only do sort of worse up to this notion of regret. If we sort of change the notion of loss to be like a non-quadratic loss, I believe like an L1-like loss was placed here. Here we sort of really see the power of GPC because you're taking gradient through that loss. You get better performance than just doing a direct LQR policy on that. So if you change your loss to be a non-quadratic loss, here is where sort of GPC becomes useful. The other sort of experiment you can do is that what if you include correlations in the sort of perturbations that are driving the system? So here we sort of do this Gaussian random walk perturbation. So the perturbation is not an independent Gaussian at every time step. It's actually it's a Gaussian random walk. So it depends on where you were last time. LQR, of course, performs badly in this because it breaks the assumption. GPC performs much better. And if you just reparameterize the system correctly, this will still be a linear system. So when I say LQR, it's in the standard parameterization of the system. But if you sort of reparameterize the system correctly, it is still a linear system. And the black line show what's the optimal choice with respect to a linear system of this modified linear system. So black sort of consider the optimal thing you can do in this thing. Red is GPC that does as well as the optimal thing. And the standard LQR fails. A similar thing is seen here if you sort of add sinusoidal perturbations. So your perturbations are highly dependent in time. They're in fact a sine wave. And again, we see sort of GPC outperforming LQR significantly. And in the same setup, we also experimented with simple things like what if you provide no control, or sort of if you look at H infinity control in this setup, and what we get is that GPC sort of is better than all of these things. Okay, so these are sort of simple systems that we did these experiments on, but these sort of verify the theory that we presented. Okay, so that pretty much concludes the first part of my talk and sort of the major part of my talk. I guess I'm not going to be able to get to part 3, but let me just quickly sort of talk about the second part, which is this problem of tracking. So this tracking problem was introduced by Kalman, maybe even before, and the idea is pretty simple. So it's going to be...
Before you get started on that, there's just a comment in the chat.
Sure.
Which is that GPC also refers to generalized predictive control from the 80s.
Oh, okay. So we should, okay. So we should clarify that. We didn't know about that. Thanks for the comment. But we really just called it gradient perturbation controller, but that's a good point. We should reconcile this. Thanks. Okay, so the tracking problem. So the tracking problem is going to be a specification of the problem that I mentioned before. And the idea here would be to get a much stronger result than we did before. So in the tracking problem, again, it's an online game. But now you pick an action and the adversary just picks sort of a reference state, right? So imagine flying imagine tracking something, right? So imagine a drone that's flying in the air and you are sort of trying your drone, trying to track this. And this red adversary sort of chooses the position of the drone that you're trying to track at every point of time. And the cost that you suffer, let's say, is just some distance between the state your system is at with respect to this reference state, and some may be potentially cost on like the control. And here, sort of, we're going to go back to the world of stochastic noise. So imagine the noise was stochastic. Then sort of this is sort of the canonical tracking problem that's been studied. The only difference here is that these XD stars could be chosen sort of in an online fashion. So they can be chosen by adversary. It's not a trajectory that's been given to you beforehand. It's a trajectory that's been decided for you as you're playing the game. So that's why you're trying to control a noisy linear dynamical system with changing convex costs. Okay, and naturally here, since the noise is a Gaussian, independent Gaussian, now you should expect all of your notions to be in expectation. So you can define a similar notion of policy regret, but now you take appropriate expectation over the generation of these noise. Okay, so over the process that's generating this noise. Okay, so this is often called a pseudo regret because the expectation lives inside the minimization, but that is the target that we are going to, that's what we're going to target in this tracking problem. And sort of the main thing that is going to be different, apart from the fact that the noise is stochastic, is now that this kind of loss function, this sort of L2 error loss function, is in fact strongly convex in the state and the control input. So that's what's going to differentiate. Like I can actually, the result will hold for any strongly convex cost on top of XT and UT. But to motivate it, I like to just typically keep it just the L2 loss. And that's what's going to be the main ingredient here. Strong convexity is what's known to sort of give rise to...
Let me interrupt you for a moment here.
Sure.
This is mainly for the speakers. So we're at 2:57. So if you have to get to a class or something at 3 o'clock, now is the time to do it. But we can keep going for a little while because, I mean, if you don't have anywhere to be, you can just stay around. And if Naman, if you're happy to talk further, we're happy to listen further too.
Okay, sounds good. I'm very happy to talk further.
Great. For those of you who do have to leave, we are recording and we'll post within the week onto our YouTube page.
Okay, so I'll continue. So so strong convexity or sort of curvature in your loss functions is known to give you much better rates than this like 1 over square root t. Remember I said 1 over square root t is a tight rate. That's only if your function has no curvature. Like the way to actually show it is this like collection of these linear function kind of functions. But in fact, if your functions have curvature as like these L2 square functions do, you can show in the standard convex optimization setup that your regret rates can go down at like your regret can be logarithmic in t. The way to think about it is that the average regret is going down as 1 over t instead of say 1 over square root t before, right? So in typical convex optimization, if your functions had curvature, you could leverage it. So what would the result here be? Naturally, can we leverage it if we know that sort of these costs that are happening, this C sub t is a strongly convex cost, or let's just say it's the L2 square loss I defined before. So what we get is this nice sort of logarithmic regret rate for the case of control with changing costs. I'm just going to refer to some like previous work here, the previous work of Abbasi at Corey et al. And Cohen et al. Had actually considered this problem before, but they had taken a slightly different sort of dynamic programming based approach, which sort of leverages, so like Cohen et al. Specifically leveraged this sort of SDP reformulation of these problems. And somehow that reformulation sort of, at least in this context, loses this notion of curvature. For the exact same problem, they were only able to show a regret rate of something like square root t. Whereas if you leave this sort of in this linear parameterization like we did, you get these like fast rates, like these sort of polylog n t rates. Okay, so that's the main result. I'm not going to get delved as deep as I did in the previous one. I'm just going to lay down what the key challenge in this sort of in this part of the in this result was. The main thing was that you know like naturally you would feel if the costs have become strongly convex, you would expect log rates to hold directly from the previous result, right? At the end of the day, we did completely an online convex optimization reduction before, so you would think that the same gradient descent algorithm, if it gives you logarithmic regret rates in the case of online convex optimization, should give you logarithmic regret rates here too. The only catch is a subtlety. Notice that we did not assume we only assumed strong convexity in the space of control and states. I did not assume strong convexity with respect to my parameterization of the policy. So this is kind of like easy to see. Like notice I have over parameterized my policy space, right? So instead of K, which was just an action by control matrix, I have over parameterized my M to be like action by control times log T parameters. So there is absolutely no way I should expect strong convexity to prima facie hold, because I'm using more parameters. How can I get curvature in every direction, right? So so this seems like a prima facie challenge. If you dig into this a little bit more carefully, here is where sort of your noise helps you. So remember, I assumed that my noise process was generated by an independent Gaussian. If I didn't say it before, I want the covariance of that Gaussian to be, say, like the natural assumptions would be that it's identity. We need the covariance of this Gaussian to be sort of lower bounded. And once you sort of do that, if you sort of see this entire thing in the in the right light, this exploration, sort of the coverage that is built in through noise, saves you and sort of gets you back into the strong convex. So what we show is that this cost function continues to be even strongly convex even under this parameterization. Notice again, my cost function is an expectation over the noise, and that's what's strongly convex. The individual one, of course, will not be strongly convex. The expectation over the noise is what becomes strongly convex. And then you can sort of define sort of in a similar way, you do the same reduction, and then you do a standard gradient descent like algorithm. Okay, so that's it. So that kind of ends sort of this part of the talk. Let me just say, because I promised about it, these works sort of appeared last year, what I've described on in the talk today. Ever since then, sort of our group has followed up on sort of shaving off each of the assumptions that I had made one by one after the other. They tackle unknown systems, they tackle partial observations. In a very nice paper recently, Max Simkowitz also showed that you can get log rates for adversarial noise situations. This comes in only for quadratic costs. You can also have slowly changing systems in a notion borrowed from adaptive regret. And you can also tackle the case when you do not know, you do not know the system, and you also do not know a stabilizing controller. So these are references. I'm happy to talk about these later also if needed. Something that we've been working on, which is in the work, something that we're excited about, is also to how to extend these kinds of notions to the sort of problem of planning. So planning means that you're going to play this game in a repeated fashion multiple times, and can you what kind of robustness can you show in the case of planning? This is upcoming work. Let me also make a since I'm recording work here, let me just also make a mention of these other works that are extremely related. I'm happy to send these slides over. These are hyperlink references that you can look at. Okay. So I also plan to talk about the boosting, but let me just actually skip over it for now. And let me just so that people can leave, and if there are people left behind, we can talk about the boosting thing as well. In summary, we propose this online non-stochastic framework for control of dynamical systems, and we gave this efficient gradient-based, what we call GPC, gradient perturbation controller. In the case of the tracking problem, where you go back to the old problem of tracking, we were able to get this log regret. And what I wasn't able to describe is this extension of boosting for control. The code for all of this can be found at that GitHub link. If you these are links for more information about non-stochastic control or just OCO in general. If you have lingering questions, comments, please feel free to email me. If you want a copy of the slides, please feel free to email me. I'm happy to send them over. Thanks.
All right. Thank you very much. That's super interesting. I have to think about this a little bit. I'm kind of surprised that it's possible and that I should have been following this literature more closely. So if you have any questions, you can just turn on your microphone and yell, or type in the chat, or raise your hand, however you want. I'm going to use host privilege and start out by coming back to this issue of someone asking the question about whether this encourages you to just have a pessimistic policy.
Mm-hmm.
So I'm trying to wrap my head a little bit around why this isn't why this can't really force itself to really go after the worst case, just protecting itself from the worst case behavior.
Right. So, well, okay. I have a short answer to that. As we the experiments that we kind of showed that okay, even when you have this, so maybe experiments is a good proof, but where was the experiment? Let me just show. So here's a standard setup, right? So if you go with if you feed the algorithm something like Gaussian perturbations, what you get is it's not doing much worse than what the optimal thing there does, right? So up to this regret rate, I guess the way to think about it is that if say let's take the case that if your noise vectors were generated out of this Gaussian, right, then what the optimality guarantee says is that up to that regret rate that you're getting square root t, you will be close to the optimal linear. In that case, the linear policy is optimal, and up to that first factor of regret, you will be within that range. So you are really not if you think about it, if I am allowed to design W's to be horribly bad, then my total cost can be way worse than just having Gaussian noise. And up to that regret rate, since you stay close to that, naturally you get this kind of adaptive behavior, which in case these W's are chosen adversarially, are they, if they're chosen bad for you, then you will truly be pessimistic. I mean, you cannot beat the bound that you get out of H infinity control. It's a min-max bound. So you will be pessimistic in the case when nature is being adversarial to you. But
yeah, so I guess maybe I can summarize by saying you'll have to be pessimistic when you have no choice but to be pessimistic. But if you're in an optimistic world, you'll be optimistic.
Exactly. And that's kind of what motivates the regret-focused research that we did. It is truly the case, you want to only be pessimistic when you need to be pessimistic. If you can be sort of better, let's just be better.
All right. Does anyone else want to jump in?
Hey, thanks for the talk. Hello.
Yeah, hi.
Yeah, I'm gonna chat with you after the talk. This is Mariam. I had a few questions. One thing was about extensions to the case where we don't know the system. Can you briefly comment about that? Because your disturbance feedback approach relies heavily on the fact that you know AB, you compute W, and you find basically the disturbance, and then you so I guess you have to do some sort of zero order estimation of the gradient, but I don't know how, like I want to know how you do it using the disturbance feedback approach.
Right. So I link to sort of the case that what you kind of need to do in the case when you do not know the system, like it's kind of unavoidable. You have to put like some kind of sys-ID to happen before you could get anything.
Right.
So you would have like the paper by sort of my advisor Lad, Karan, and sort of Sham tackles this exact problem. Even under adversarial noise, you will have to define a notion of sys-ID to happen first. And once you've got your sys-ID, then you can sort of.
Okay, all right. So first you identify the A and B.
Yeah. It turns out like that's kind of, at least that's what the best way we know how to go about this.
Okay, and then I had another, if I may, another question about your comment you gave about the strong convexity, which I am not sure about the comparison you made because, well, the CTs were strongly convex in X and U, which is not a priori obvious that once you do the disturbance feedback parameterization, you have a strong convexity. But then you said that, you know, the K has, I don't know, reduced number of parameters compared to M by the order of time, right? But the cost originally is not even strongly convex in K. So is that a good comparison? Because it's polynomial. It's a polynomial in K, high order, not like based on the.
That's a good point, indeed. That's a good point. I guess what I was trying to show is that I guess maybe that was maybe a way to show, okay, there is a certain amount of over-parameterization happening here, even beyond. But you're right to say that the cost is absolutely not convex. Like it's not even convex in the parameterization of K, so forget strong convexity. But yeah, it's even the K is kind of over-parameterized for it, right? Like it is strongly convex in the dimension of D, but K lives in sort of D by D. So it is sort of over-parameterized even in terms of K. So to answer your first question, why do you get strong convexity? The way to think about it is this, okay? So think about like your cost being just an L2 cost on U, like an L2 square cost in U. And think of putting an expectation over the noise vectors, right? So now your policy is going to look like M times W in a product with itself. And then you take the expectation over W, right? And this is where sort of the independence assumption on W is going to hit. And what you're going to get is that this thing still looks strongly convex in M.
Okay.
Right. This is a like, I mean, it's quite an easy calculation to actually just perform. But
the cost is a strongly convex in M. I mean, your first part of the talk, that's you have a strongly convex cost in, if C is strongly convex, would you have a strongly convex cost in M? This is related to the first part of the talk.
So in the first part, no. When you've got adversarial perturbations, there is absolutely no way for you to show that. Like if W's are chosen sort of not in sort of the stochastic manner, then you will not have strong convexity.
But W is fixed in your inner problem. W comes after. The max over W is afterward.
Right. So for every sequence, for any fixed sequence of W, there's no strong convexity. It's only when I take an expectation over the sequence of W that expected cost is strongly convex. For any single sequence, it's not strongly convex. So indeed, like because you raised this point, in the second case, your algorithm, which is taking a gradient, now has to take the gradient over the expected cost, not a single realization. But then you could, like, because we know from machine learning, stochastic gradient works, you could possibly just do multiple, like, a few rollouts, and hopefully that's a good approximation of your expected cost, like the good approximation of the gradient of your expected cost.
Oh, thank you. See you later.
So let me just say, you don't have to be a faculty member to ask questions. And particularly if you're not a faculty member, I would say that a lot of the faculty members who attended the talk probably want to understand this better too, if that's what you're thinking.
So I'm going to go ahead and ask a question. Hey, Norman, I'm going to be selfish and then ask you to maybe you can help with my research question. How you can attack problems, but the time horizon is not finite. Like,
Nice question. So this is something that you would like. The way you would tackle this is so the general online convex optimization. That literature itself tackles this problem by this. There are multiple ways to sort of tackle this problem when you do not know the time horizon in advance. But one sort of way to do this is via a thing that's called the doubling trick. So like, because like what happens is that your sort of step size, the optimal step size that you're going to pick is going to depend on like sort of your time horizon, right? So what you do is sort of you sort of expect, let's say you expect your time horizon to be 10, right? But then sort of you make a conservative choice with respect to your 10, but then you see that sort of your time horizon is growing larger, so you sort of make it 20. And then you choose the rest of your learning rates to be focused with respect to 20. And this sort of what you can show is that as you keep doubling this, overall the effect of this is only up to a constant.
Okay, I see. Thanks.
Can I ask a follow-up on that? In the OCO literature, doesn't the step size usually depend on the time? So aren't those results usually assuming you're doing like a fixed number of steps in some way?
Yeah. So usually they like that's like you can get so okay. So firstly, a few things. I mean, typically it's a simplification to show that those results depend on time. Many of those results actually are fine with a learning rate of something like 1/√t or something that scales like that instead of actually being capital T. But that's kind of like the continuous way of getting that to work. The sort of the janky but efficient way of getting that to work is like, if you don't know the time step ahead in time, just think of it as something, say whatever, 10, 15, something, and then keep doubling it. Like every time you've played the game beyond 10, think that it's 20, then think that it's 40, and then keep choosing your learning rates appropriately. And this, you can show that this thing doesn't screw you up more than a constant factor or something like that.
I have one more question, but if anyone else wants to jump in, feel free. You have 5 seconds. Okay, I want to ask something that's kind of related to Miriam's first question, which is, so she said, what if you don't know the system? So let's say you do know the system, but the dynamics are not homogeneous across time.
Yeah, that's a good,
and I know you have an easy answer to that one. So let me make it a little bit more complicated. And let's say the dynamics can also depend on the state you visit.
Okay, let me answer these questions in order. The first question where you say that the dynamics can change across time, but let's say that they are independent of the state that you're going to visit, right? We don't have a formal guarantee written up, but we sort of believe that like you'll have to allow for certain changes to happen, because then like notice that somehow the optimal, like this is called the non-stationary case in like in LQR literature, and like in that case there is no stationary policy that gives you the optimal anyway, even under something like Gaussian noise. Like it will be a non-stationary policy. So like you can get results similar to like if you want to compare to a stationary policy there. We didn't write it up because it's kind of like, like it's not clear completely, but like in terms of implementing an actual algorithm out there, I believe the algorithm doesn't need to change. Like if you implement this correctly, it'll be a good algorithm even in that case. Proving bounds could be here, and like you'll have to maybe make certain assumptions which could be kosher, not kosher. So that's why I guess we never really formally sat down to prove bounds in that case. There is another piece of work that I pointed to, which might be interesting in this regard, is there is in online convex optimization, there's a certain notion of adaptive regret. So what you like there, you don't really want regret over the, like you want a stronger guarantee than regret. You want regret to happen sort of over every small subinterval also. And in that case, if you've got if you've got a guarantee that like your systems are sort of changing slowly, so a sub t, like instead of a, it's a sub t, and it's drifting slowly, they handle things related to that. Like that paper actually handled things related to that. Your second question, if the system depends on x sub t, all bets are off. Like that one's the real that one's the real hard case. Like that's a truly hard problem.
Like that's almost getting into like p-space hard issues. So I'm just wondering sort of like where the boundaries are between like where it's possible to do regret and where it's possible that maybe you just can't found regret.
Let me also point out something that the case that you point out actually brings out like maybe a potential negative in our framework, which says that when I define my counterfactual sequence in my regret, I use the same sequence of perturbations to define the counterfactual sequence. But then if your states are like if your system's depending on your state, you should allow your perturbations to also depend on your state, and that's where a guarantee breaks. Like we don't know anything to like. This is a good.
That's again getting into like interactive proof type territory, because now your adversary's policy has like exponential size.
I think it's almost like anything reasonable that you want to say in that is almost easy to show that that's not going to work, basically.
Fair enough. Okay. All right. Thank you so much. This was super interesting. I thoroughly enjoyed it. I want to go and read all your papers now.
Okay. Thank you. Thanks.
People left, but let's do a virtual applause and then send you on your way, I guess.
Okay. Thanks, Mark, for inviting me. The questions were great. Thank you.
Perfect. Thank you for joining us. And Mark, thanks for hosting. It's great.
Thanks, Aaron.
Thanks.